Hello and welcome to the Superposition Guys podcast. My name is Yuval and my guest today is Pierre Desjardins, co-founder and CEO of C12 Quantum Electronics, a company using carbon nanotubes to create a new quantum architecture. Pierre and I talk about their unique technology, what carbon nanotubes are, designing custom application-specific quantum chips, and much more. We hope you enjoy this episode. Hello, Pierre, and thanks for joining me today.
Hello, Yuval.
So who are you and what do you do?
So I'm Pierre. I'm the CEO and co-founder of C12. And C12 is a Paris-based quantum hardware startup. So we are leading the next materials leap in quantum computing. And let me start with maybe what happened in the early days of classical computing to better explain what we are building. So in the early days, the digital computer were made with vacuum tubes, and vacuum tubes they could not make at all today's smartphone. And what is missing is the silicon transistor. So at C12, what we have is a quantum transistor, and it's made of a carbon nanotube. And we think that it's the way to go to build like a large scale and performing quantum computer.
In C12, the name is because that's the carbon isotope C12.
It's indeed right. So our approach is really to have the cleanest and the purest material for encapsulating our qubits. And this vision is really because at the end, the quantum errors, the quantum that the whole industry is fighting against, they're coming from defects in the qubit material, in the material. So the cleanest and the purest is your material, the easier is to have like a very good fidelity for your quantum computation. Means like a very good quality for your qubits. So if you take spins, indeed you have a lot of errors that comes from all the spins that are close to your electron. And those other spin they come from nuclear spin. And if you take the isotope 12 of carbon, then the number is even, and so you don't have a nuclear spin. And what we are working with is isotope that are purified at 99.99%. So it's extremely high. And at the end, what we calculated is that we have less than one nuclear spin on average per qubit. So it's like this is what we mean by a very clean material.
When you say the number is even, do you mean that there are 6 protons and 6 electrons, or is it something else?
I guess this is no. So when I say 12 is the atomic number for this isotope. So it's the same number in the nucleus.
Excellent. Carbon nanotubes. That they sound small. How small are the nanotubes, and how do you make them?
So they are indeed extremely small, and I think it's a big advantage when you scale a technology like we do. So we can make them as long as we want, but usually we are using like a few microns for their like really active sites, and in diameter they are between 1 and 3 nanometer. So it's extremely small. And what is important is only a single layer of carbon atom roll over itself. So it means that at the end, it's only a few hundreds carbon atom that where we trap our spin qubit. Because what is actually very exciting about this technology is to have this incredibly pure material, but is also our ability to integrate this carbon nanotube on silicon chip, like the same chip as the one that you use in your smartphone or on your laptop. So we start with those very standard CMOS chips, and we are able to make them quantum by integrating this like incredibly pure quantum element, the carbon nanotube.
And the qubit inside the nanotube, what is that atom made of? What is that atom inside the nanotube?
So it's we use an electron, not an atom, and actually we use the spin of an electron. So it's the most natural system to make a qubit because it's naturally a two-level system, and also it's well isolated from its environment, like naturally. So the quantum computer that we are building is really relying on the first principle laid on by Loss and DiVincenzo when they describe the theory of a quantum computer.
Now, quantum computers do the computation by having the qubits interact. So you have individual spin tubes and individual carbon tubes, and inside them you have an electron. How do you get the individual qubits to interact with each other?
Yes, indeed, because the power of a isolated qubit is not making a quantum computer. So what we have is a quantum. We call this a quantum bus. So it's like in the classical word. So it's a communication bus that linked all our qubits. And on this, it relies on something that has been demonstrated in the lab we are coming from at the École Normale Supérieure in Paris. And it's called a spin photon coupling. So the way that you can actually couple a spin hosted in a carbon nanotube with the photon in this quantum information bus or quantum communication bus. And this is where it's actually becoming very interesting. So instead of other solid state qubit technology, we then are not limited to have only the qubit connected to its closest neighbor. We have like much more flexibility in our design, and we can really like design some qubit architecture, some layout where you have like more connectivities than just a connectivity to your nearest neighbor, thanks to this like a very important like quantum communication bus.
Can you give me some numbers? What do you have in the lab, or what do you have working in terms of the status of the product to begin with, and how many qubits have you demonstrated? What kind of gate fidelity, if you can share? Any numbers would help.
Sure. So what we are focusing right now is really about a single qubit devices to. So I think that compared to other, let's say, commercial companies, we think that quantity is not the only metric that matters, but quality is even more important. That it's more difficult. Probably it's hard for everyone, but it's more difficult to focus first on the quality and then focusing on scaling the technology. So that's why we are like focusing on single qubit devices. And so we are working on two things. So increasing the coupling, so how fast we can drive the spin, and also the current time of our spin qubit. So these two developments are like really at the core of our tech roadmap. So the key result that we will soon publish is about. So we computed the fidelity that we can get with our technology, given like really where we are right now and realistic assumption about our components. And so we can achieve 1 qubit gates with a fidelity of 99.99%. And for the 2 qubit gate, we have a lower bound at 99.5%. So I think this is very promising. but of course, we are still working on these developments.
And who would be your customers? So would this go into someone who wants to make a quantum computer, or do you intend to make your own quantum computers?
In terms of product, so what we will deliver, it's the chip and the low-level control software. So in terms of positioning, it's really close to what NVIDIA did in the GPU market, where they were able to offer like very high performance GPU chip, but also this low-level control software, which is CUDA. And so we have this strategic choice of not being full stack. We think that a lot of value is actually in the hardware, and this is the key bottleneck right now in quantum computing. And so we are also like partnering with some partners on companies developing quantum algorithm, quantum software, and we think that it's really the way to go. Like in our strengths is and our expertise is on developing incredibly performing quantum computer, quantum chips, and some other company are really good at developing quantum development kit and also like quantum algorithm.
Does your system still need cryogenic cooling?
It does, yes. So one thing we have to think about is cryogenic is a problem if your qubit is really big, like for superconducting qubit. Because in this case, when you scale, the volume that you have to cool down is rapidly becoming gigantic, like the size of a soccer field. But our qubit is like 10,000 times smaller than a superconducting qubit. So at the end, I mean, we don't have like a bottleneck in the near term on cooling power.
Now, there are many companies who are making quantum computers, and they have different modalities. Of course, superconducting is one of them, but you've got trapped ions or neutral atoms and photonics and so on. How do you plan to stand apart to create a differentiation from these companies?
So no, I think that what is interesting is that we have very unique approach. So if you look at what is the core strengths of other technology, if you take first, for example, atoms and ions, they are super good because their qubits lies in vacuum, so they are extremely well isolated. They can have like high fidelity, but we know that it's really hard to scale them like above a threshold that is maybe at 1,000, maybe a bit more, but we know that it's going to be very hard for them to scale. If you take on the other side, like superconducting qubits, they rely on semiconductor devices and fabrication, so it's much easier to scale, but they are like really at their limits in terms of current time. So that's why actually there's this huge effort about error correction. But error correction would be so much easy if you have like better qubits. So really what we offer with C12 is like to combine like best of those both approaches, like the compatibility with semiconductor devices with this ideal architecture of a spin qubit in vacuum.
At what stage is the company? If you could tell me a little bit about number of employees, perhaps, or money raised, or most importantly, how close are you to having a product that customers could use?
So a lot of question here, but so we funded the company 2 years ago in 2020. Maybe worth mentioning that we funded the company with I funded the company with my twin brother Mathieu. So Mathieu is really the scientific mind behind the technology, and I'm more in charge of business development. So we raised last year our seed round with a total of $10 million. It was led by 360 Capital, which is a large European deep tech fund. And on board, we also have like Airbus Venture, BNP Paribas, which is like one of the largest global bank in the world, and BPI France, which is a French state fund. So now we are like 30 people. And in terms of commercial products, so the first product that we will offer is C12 simulator. And this is quite exciting. It's really like a digital twin of the chip that we are building. And actually, a lot of people want to understand like when the some hardware will be ready, what kind of algorithm they will be able to run, what kind of application they will be able to perform. So this will be the first product, and we will announce it very very soon, the release, and it would be accesses directly through the cloud. And then we will focus on near-term applications. So we think that we don't have to wait like 10 years or more, and we don't have to wait for error correction to have like a useful application. And especially if you look at chemistry application. So that's why we are actually already launching some project with some customers about designing those first quantum processor that will help them on some of their critical chemical processes. So we have one project with Air Liquide, which is a global gas and service company, and so with them, we are first identifying the right application we want to focus, and then designing the right layout for this application before like actually delivering them, which will be in a couple of years, the actual chip.
So are you saying that the chips are essentially customized to the particular application, whether it's the connectivity or number of qubits or something else? So one chip per a type of application?
Yes, you got it right. It's if you want to really like get the most performance possible from the early quantum computers, it's very interesting to have this customized approach. So we call this application specific design. And indeed, there is a couple of parameters that you can actually modify in the layout to really minimize, optimize the quantum resources that you can offer for this specific application.
Can you give me an example? For instance, how would a chemistry application be different in terms of the chip layout or resources from, say, an optimization application?
So I think it's we are like so right now C12 is we are holding like 6 patents. So both on like fabrication and also design. But on this specific thing that we are like still like writing the patent, still in the patenting process. So I will have to be a bit vague, but what is important, of course, is that you can customize the number of qubits. For example, if a qubit is like really rarely used in your computation, maybe you can actually skip it. We can also change the connectivity between the qubits. So you can have like all of them connected together, but maybe it's like actually something that you don't really need. So then you have like some more advanced design where only you use only part of the connectivity that you need. And of course, also we are like working on special gates that can be very useful for quantum chemistry application.
So when you say special gates, do you mean beyond 2-qubit gates? Do you mean multi-qubit gates or something else?
Something I need to stay vague about.
Very good. So as we get close to the end of our conversation, I want to go back to the beginning and ask you again about carbon. What is unique about carbon that made you choose that and not some other element?
So one answer is in our name is the fact that you can really like get a very pure isotope of the carbon. The other thing is, of course, that you can grow them in carbon nanotubes and have them suspended over your chip. So this suspended thing is really interesting because then you have like a vacuum around your hosting material, which is as shown with atoms and ions are extremely good for qubits.
Excellent. So how can people get in touch with you to learn more about your work?
So we have this spent some time by designing our website. So c12que.com. And what so you have a lot of information about quantum computing, but also our technology and really how it works, how we fabricate our chip, how we operate them. And of course, we are hiring. So on this website, also you will see all the different positions that are available right now at C12. So if you are you want to join the quantum race and you want to actually build something very unique, please let us know.
Excellent. Thank you so much for joining me today.
Thank you so much for the invitation, and that was a pleasure to be there.